Hello, this is the section 5.3 to 5.4 lesson. In this section we're going to talk about a specific type of random variable and its associated probability distribution. Now for this lesson you're going to need your calculator. The type of random variable and distribution we're going to talk about in this section is called a binomial random variable, and the associated distribution is called a binomial distribution. A binomial distribution describes a procedure that meets the following requirements. Number one, we have a fixed number of trials. That means that we repeat some activity over and over again. Number two, the trials must be independent. That means that what I get on one trial has no effect on what I get on any other trial. Number three is the most important one. Each trial has only two events, commonly called success and failure. Two events is where the bi in binomial comes from. Now a success and a failure are very generic terms. Success generically means that we observed whatever it is we were interested in. It doesn't necessarily mean that something good happened, nor does failure mean that something bad happened. And then number four, the probability of a success remains the same in all trials. So the probability can't change from one trial to the next. So as an example, suppose we have 5 children and we're interested in their genders. Here we have 5 trials. They're independent because the gender of one child has no effect on the gender of any other. We have 2 events, either boy or girl, and we'll call a success a girl and a failure boy. Again, we don't mean that one is good and the other is bad, just means that we're interested in girls in this case and we're not interested in boys. And then fourth, the probability of a success or the probability of a girl is 1/2 in all trials. So what this illustrates is that the number of girls in these 5 children would be a binomial random variable, or state another way, we can use a binomial distribution to describe probabilities in this example. Another example is one that we saw in last section. Suppose we choose a jury of 12 from a population that is 80% Mexican American. In this case we have 12 trials. Each person that we choose would be a trial. They're independent because the nationality of one has no effect on the nationality of another. We have 2 events. Either the person is Mexican American or they're not. Now that not category combines a lot of different nationalities, but we'll just combine them into one big category. We'll call a success a Mexican American and a failure not Mexican American. Again, we're not implying that one is good and the other is bad. And the fourth, the probability of a success or the probability of a Mexican American is 0.8 in all trials. And it's equal to 0.8 because our population is 80% Mexican American. So the number of jurors on this jury of 12 would be a binomial random variable. State another way, we can use a binomial distribution to calculate probabilities. So some questions we might ask in these 2 examples. In the first one, having 5 children, what's the probability of having exactly 4 girls? On the jury, we might ask what's the probability of getting exactly 9 Mexican Americans on our jury. We can use a binomial distribution to answer these 2 questions. We're going to talk about some notation here before we introduce formulas. Let's let n be the number of trials. Now before we let n be the sample size, number of trials is going to be very similar. X is the number of successes. Now x is our random variable here, so it's the number of successes out of our n trials. Now x can take on values only between 0 and n. We can't have a negative number of successes, nor can we have more than n successes out of the n trials. Now x definitely has to be an integer, but it can only take on values between 0 and n. P is the probability of a success in one trial, and Q is the probability of a failure in one trial. Now once we know P, we can easily calculate Q by simply 1 minus P equals Q. And then capital P of x is the probability of exactly x successes among the n trials. We saw this notation P of x in last section. Here P of x has a similar but slightly different meaning. So here's our formula for calculating P of x in a binomial distribution. It's n factorial divided by n minus x factorial times x factorial times p to the x times q to the n minus x. Now this formula is a probability distribution in the form of a formula. A formula like this is what's called a probability density function, or abbreviated PDF. Now this formula looks a little scary. It is a little complicated to use, but luckily it's already built into our calculator. But let's just really quickly illustrate how this formula is used. So in our scenario where we have 5 children, let's calculate the probability of exactly 4 girls. So in this case n is 5 because we have 5 trials. X is 4 because we're considering a success having a girl, so we're interested in the probability of 4 successes. P is 1/2 because the probability of a girl in any one trial is 1/2. And then Q is 1 minus 1/2, which equals 1/2. So the probability of exactly 4 successes, or P of 4, is equal to, you see the numbers plugged in there, n factorial divided by n minus x factorial times x factorial, etc. You see the calculator commands there on the right, and the probability is 0.156. So again, that's the probability of exactly 4 girls in a family with 5 children. Now again, luckily this formula is built into our calculator. To access it, hit second vars. Vars is right next to the clear key, and then you get a catalog called distribution, or DISTR. Under distribution is scroll down to option A, which is binom PDF. Binom PDF stands for binomial probability density function. Now when you select that option, back at your blank home screen, it will paste binom PDF and then an open parenthesis. And then you need to enter n, comma p, comma x. So in this case n is 5, so hit 5 and then comma key is right above the 7 key. And then 0.5 because p is 0.5 in this case, and then comma x is 4 in this case, so enter 4 and then do a close parenthesis and then hit enter, and you see our probability there, 0.156, which is identical to what we got using the PDF formula, but this is a lot easier to enter. As another example, let's consider this procedure, choosing 12 jurors from a population that is 80% Mexican American. Now in last section we saw a probability distribution in the form of a table for this procedure, and let's look at how we can calculate these probabilities using our calculator. Okay. So again, we've already mentioned that this x, the number of Mexican Americans, is a binomial random variable. N is 12 in this case, and p is 0.8. So to calculate, for instance, the probability of exactly 7 Mexican Americans on our jury, we would enter our calculator the first command that you see there, binom PDF 12, comma 0.8, comma 7. 7 because we're interested in exactly 7 Mexican Americans on the jury. You hit enter, and you see the probability is 0.053. Now if you compare that to the number in the table, you see that it's identical. Go down to x equals 7, the probability is 0.053. If we want to calculate the probability of exactly 11 Mexican Americans on the jury, I'd enter binom PDF 12, comma 0.8, comma 11, hit enter, and the probability is 0.206, which again agrees with the number in the table. Again, this just illustrates that these probabilities in this table were calculated using the binom PDF formula. In last section we noted that every single random variable has 2 associated parameters, the mean mu and the standard deviation sigma. Here were their formulas for calculating them. The formula for mu was not terribly complicated, however the formula for sigma was rather complicated. For a binomial random variable, the formulas are quite a bit simpler. Mu is simply equal to n times p. Sigma is the square root of npq. And we also mentioned in the last section that the mean mu is also called the expected value e. In binomial distribution, the expected value has a very specific meaning. The mu, or expected value, is the expected number of successes in the n trials. So for selecting the jury, let's calculate the mean and standard deviation. Here n is 12, p is 0.8, q is 0.2. So mu is simply 12 times 0.8, which is 9.6. And sigma is the square root of 12 times 0.8 times 0.2, which is about 1.4. And you see the calculator commands for finding those values. Again, the mean mu is the expected number of successes. In terms of our jury, that would be the expected number of Mexican Americans. Now, it's impossible to get exactly 9.6 Mexican Americans on our jury, but a mean is a theoretical number. It's not something that we actually expect to observe. Standard deviation doesn't have as nice an interpretation as the mean. However, it does have its uses, and let's look at one use of it. Back in chapter 3, we introduced the range rule of thumb, which said that the maximum usual value for a set of data was mu plus 2 times the standard deviation, or the mean plus 2 times the standard deviation, and the minimum was the mean minus 2 times the standard deviation. Well, we can say the same thing about a random variable. For a random variable, its maximum usual value is the mean mu plus 2 times the standard deviation sigma, and the minimum usual value is the mean minus 2 times the standard deviation. So for selecting our jury, the maximum usual number of Mexican Americans would be the mean 9.6 plus 2 times the standard deviation of 1.4, which comes out to be 12.4. So that means that anything greater than 12.4 would be considered unusual. Now, it's impossible to get more than 12.4 Mexican Americans on a jury of 12, so that number really isn't meaningful. However, the minimum usual value is 9.6 minus 2 times 1.4, which is 6.8. So anything less than 6.8 would be considered unusual. What this means in more practical terms is that getting a jury with 6 or fewer Mexican Americans is unusual and would indicate that the jury is not randomly selected. Now, in the previous section, we did an example using the rare event rule, where we concluded that a jury with 6 Mexican Americans is indeed unusual. That is an unusually low number of Mexican Americans. Here, the range rule of thumb just confirms that conclusion. Now, here we're going to look at one last example that's going to illustrate a use of the range rule of thumb. It's also going to illustrate an example of inferential statistics. Here we're going to use some data from a sample to make a conclusion about a population. And specifically, we're going to use some data to test a claim. And this is similar to what we're going to be doing frequently starting in Chapter 8. So Mars Incorporated claims that 14% of its M&M plain candies are yellow, and a sample of 100 such candies is randomly selected. Part A, we want to find the mean and standard deviation for the number of yellow candies in such groups of 100. Well, before we start doing calculations, let's make a couple of observations. First, we have a procedure here where we choose 100 M&Ms. And this is a procedure because we don't know what we're going to get until we actually do it. Okay? Each M&M is either yellow or not, so we have two events. The color of each is independent because the color of one has no effect on the color of another. We have 100 trials because we're choosing 100 individual M&Ms. And so the number of yellow candies in such groups of 100 is a binomial random variable. So we can use binomial distribution, the binomial PDF, the formulas for the binomial parameters to calculate things like probabilities and means and standard deviations. So we're working with a scenario here that's described by a binomial distribution. So if we consider a success selecting a yellow candy, because that's what we're interested in, n is 100, p is 0.14 because we claim that 14% are yellow, and then Q is 1 minus 0.4, which is 0.86. So we can use our formulas for the binomial parameters to calculate mean mu and standard deviation sigma. Mu is 100 times 0.4, which is 14. Sigma is 100 times 0.4 times 0.86. Take the square is 3.5. So a mean of 14 means that we would expect to get 14 yellow candies in a group of 100. So now part B is where our statistics, our data is going to come into play. So a random sample of 100 M&Ms contains 8 yellow candies. Now that is less than we would expect, but we need to answer the question, is this result unusual? Is that an unusually low number of successes? And then based off our answer, does it seem that the claimed rate of 14% is wrong? Okay. Well, we can use our range rule of thumb to calculate a usual minimum number of yellow M&Ms. Usual is the mean minus 2 times the standard deviation. 14 minus 2 times 3.5, and that comes out to be 7. So 7 or fewer M&Ms would be considered unusually low. Well, in this case we got 8. 8 is not less than the usual minimum. So 8 is not less than the usual minimum, so it is not unusual. It is less than what we would expect, but it is not unusually small. So what that means is that our assumption of 14% yellow candies does not seem to be wrong. We do not have enough evidence to conclude that that rate of 14% is wrong. We did get less than we would expect, but we did not get an unusually small number of successes. So again, this is the type of thing that we'll be doing quite frequently in Chapter 8. We're going to use some data from a sample to test a claim about a population. Here our claim is that 14% of the population was yellow. We had this data, or sample data, in which 8 were yellow, and we concluded that the 14% number does not seem to be wrong. Now we don't prove that the 14% rate is correct. That rate could be wrong, but we don't have enough evidence here to conclude that it is indeed wrong. So that's it for this section. The course compass homework is titled Section 5.3 to 5.4. Now in a lot of those problems it'll ask you to calculate binomial probabilities, and you can use your calculator in that binom PDF formula to calculate those probabilities. Ignore any directions that tell you to use a table to find probabilities. There is a table in your back of your book that gives binomial probabilities, but we're not going to use that. Here we're only going to use our calculator to find probabilities.